Hey, good evening, class. Adam Ward here. I want to talk with you tonight about modeling pathogens. Specifically, this evening, I want to talk through how we deal with the mortality rate that we expect for pathogens. This goes along with Lecture 27 out of your Chopra textbook. And so, when we model pathogens, we're typically thinking about that source being human-derived, so we release pathogens into the system, and we're going to focus today on what removes them. Basically, three processes. The first one is base mortality. Things die. And so Chopra uses a KB1 to represent this. That's a rate coefficient, so a per time units. And our rate law looks something like this: 0.8 plus 0.006 times PS times 1.07 to the t minus 20. And so that PS is percent of seawater in this expression. So in saltier water, we expect faster mortality. One thing I want you to just notice here, that leading edge, that's your mortality rate at 20 degrees Celsius. This is set up as an Arrhenius equation for you already with a theta of 1.07 and that exponent of t minus 20 to correct that rate law as you need. There's a very similar equation given in Chopra 27.3. It's a reformulation that instead of using percent of seawater, it corrects to salinity. Either one is acceptable, just make sure you know which one you're using based on what you're given in the problem. So the next is a function of light. So basically increased light exposure and the UV light in particular is killing our pathogens. So loss due to light. And so this one gets a little more tricky. We've got some I naught representing the solar intensity at the surface of the water, and we saw this variable as well when we did time variable reaction rates and looked at time of day and photosynthesis. That tends to decay exponentially with depth, and so just a generic exponential decay would look like this, where that z would be representing your depth. That Ke term in there is the light extinction coefficient, so how quickly is light extinguished as it goes down through that water column. And so if you're in a very turbid stream, for example, that solid red line might be what you would see rapid extinction of the light. In a very clear stream, it might penetrate deeper. So the arrow I've drawn there is increasing extinction coefficient. And so our loss due to light is going to be proportional to the average light intensity. That alpha is a proportionality constant that also fixes your units, and we typically just take that as unity or 1. And so if you go ahead and integrate that orange equation across the total depth h of your system, you get an equation that looks like this. And so again, I'm showing you in purple. All that we've done is integrate that equation across the total depth of our system. So knowing depth, extinction coefficient, and the intensity at the surface, we're able to estimate losses due to light. Finally, losses due to settling. And so I want to start here with just a quick cartoon. Picture these black circles as sediment particles. They're settling at a velocity of vs. And picture in red, I've drawn some pathogens. You'll notice there are both free-floating pathogens as well as pathogens that are sorbed onto those sediment grains. So the only pathogens who are actually going to settle are the ones who are sorbed. So all of those losses are associated with the settling of sediment grains. One of the assumptions that we typically make is that we're at a state of equilibrium, meaning if you're a pathogen and you sorb, you're not necessarily stuck there, but if you let go, someone else is going to take your place. And so we get this partitioning of pathogens between those that are sorbed and those that are free-floating. For settling purposes, we only want to deal with those that are sorbed. Now, Chopra talks you through the derivation of this in 27.3.3 in the text. I'm just going to hit the high points here. Basically, what we can do is estimate the fraction that are sorbed using an equation that looks like this. And so you've got KDs, those are capital Ks with a subscript D, and M. You remember Chopper uses M for sediment concentration. And so this KD is the sort of the only new piece here. This is a partitioning coefficient. So it basically describes if we put some water and sediment together, we mix things up, how will the pathogens partition themselves into a free-floating fraction versus a sorbed fraction? Or what kind of sorption do we get per gram of sediment that we include? You'll notice that that has units of volume per mass. That's in order to basically make your units work out. Again, M is suspended sediment concentration. And so with this in mind, we can take what we've always done, the ability to express settling as a rate coefficient instead of a velocity per unit depth. And we just have to modify that with this F sub P, or fraction sorbed. That way the only settling losses are occurring to some fraction. So that F sub P is going to range from 0, meaning everything is free floating, to 1, meaning everything is sorbed to sediment. So 3 processes. All we need to do is simply add those together. And that's our terms respectively for mortality, light, and settling. You'll notice here I use the mortality formulation for salinity. That's that capital S in the mortality term. So we can add mortality, light, and settling together. And now you've got a loss rate to describe pathogens in your system. I hope this helps you move forward with your problems. Thanks, class.